and limitations. We had to partly participate remotely, and we had to make a replacement. Alexander Borisovich Makarov, who was putting his white shirt on, he does come to rescue quite often. So he's going to present instead of the Michael Campbell originally planned to, was supposed to present at the masterclass, but unfortunately wasn't able to do so. It's an unfortunate situation, an unexpected one. So certainly this is unexpected. However, I think we can begin. Let me just briefly provide an introductory presentation regarding what we plan to discuss during today's masterclass. Just give me 1 second. I'll try to figure out how this works. I think this is how it's supposed to be. I hope you can see my presentation now. Wonderful. I would like to start our workshop today. We believe this is quite a popular topic, especially in Russia, and it's called Ground Control Management Plan, or in Russia we call it Rock Mass Management Plan. There are different abbreviations, but this is the way we decided to call it. So in terms of the speakers presenting today, first of all, let me introduce myself, Ivan Levinsky. I'm the head of the Rock Mechanics and Hydrology Office of SRK Consulting Russia. I will moderate today's workshop and potentially go into discussions. I didn't plan to have a long presentation, just give you a brief introduction, and I'll just be managing the process of today for the next hour or 1.5 as planned. As I said, Alexander Makarov helps us a lot and has been working with us a long time, and we learn from each other. So he will be making his presentation last, despite him being second on the slide. Nonetheless, I think he will conclude today's masterclass. We also have Viktor Spirin, who is our senior consultant of our Moscow office of SRK Consulting. He is going to speak about the specifics of the Russian practice. By the way, Viktor is one of few who managed to make it physically to today's hall, so he's going to be looking into your eyes, not into the camera. And Ivan Birichov is going to speak about mostly underground operations and the key factors of the ground control management plan. He is also going to be participating remote since he's on a site visit, but he managed to make time to make the presentation. Things we wanted to cover: the main topics or aspects that we want to touch upon are the components of the ground control management plan. Also, as I said, Viktor is going to speak about the specifics of applying this in Russia and the key requirements for GCMP for underground operations. And concluding my introductory presentation, I'd like to cover the main objectives that we would like to discuss. First of all, we would like to provide SRK's understanding about the importance of GCMP and the key factors in the GCMPs that we believe should be in such a plan, and also discuss the specifics and peculiarities, including the differences between GCMP for open pit and underground operations, and then talk about the specific features regarding Russian application in Russia. So from this, I'd like to give the floor to Victor Spirin, who is going to kick off the practical part of our workshop. If Victor is ready, and other people responsible for turning the presentation on. That's all from me. Thank you. Good afternoon, everyone. My name is Victor Spirin. I'm SRK Consulting Geotechnical Consultant. The topic for my presentation is the Ground Control Management Plan, or GCMP. And we're going to talk mostly about open pits and the specifics of applying that in Russia. Regarding the content of my presentation, we'll generally look at the general questions and the relevance of introducing GCMP and the key elements, but I'll talk about this a bit later. So what a GCMP is, this is a document that is created on the basis of the data obtained over the years of study and the operation of the mines, aimed at safe operation, efficient mining methods by providing an optimum parameters to open pits, benches and slopes. In other words, GCMP generalizes and accumulates all geotechnical data for the deposit and defines the relationships between different disciplines in terms of geotechnical support. Regarding the relevance of introducing GCMP, here the completeness and the reliability of the data used for design and operation on the rock mass, the safety at the operation dwells on, but there are always different uncertainties that are related to data heterogeneity and insufficient level of data and lack of information in the geotechnical models too. In other words, if we knew all the data before the design 100%, one would have been able to optimize the project without needing a ground control management plan, risk assessment and monitoring. So the objective of the ground control management plan is to introduce geotechnical support and risk management in conditions of existing uncertainties for safe and efficient operation. As for Russian regulatory documents, we recently received an updated rules for ensuring slope stability last year, and in general the concept remains the same as in other or previous regulatory documentation. So there are standardized approaches, and those are compulsory for state review, and all mining companies have to fulfill minimum requirements on geotechnical support. There are some new conditions as well regarding risk assessment and monitoring. So monitoring now isn't just now looked in terms of the mine survey, but the whole term of monitoring was expanded. So there are other untypical for mine survey department monitoring areas. So the operations now need to create monitoring teams. Particularly this relates to category 2 hazardous facilities, i.e. open pits with total material movement of over 1 million cubic meters per annum. So that's in total rock. But creating a GCMP, such a document, isn't a compulsory requirement of the current federal norms and regulations, because the document should be flexible enough to the specifics of mining operations, and it's mostly supposed to be meant for internal use and updated as required and as risks are being reassessed. I mean, geotechnical risks. So what are the key provisions that need to be included in the GCMP. You can see them to the left, and on the right-hand side, you can see the overall structure of the geotechnical support team at the operation. This structure contains such main elements as at the higher level as a geotechnical examination, so creating geotechnical models. In the middle, it's the stability analysis for pit benches and slopes, and all the assessment analysis of justifying stable parameters for final pit design slopes, and at the bottom it's the implementation with monitoring and risk assessment and justification of measures to ensure slope stability. So GCMP includes all these areas, but the first two elements are incorporated there in a generalized way with external references. And the last element, which is the project or design implementation, is reviewed and looked at more detail. And it includes the mitigation measures, information regarding the geotechnical team, document control and turnover, risk management at the operation, and other aspects related to safe operation. Let's dive into those elements a bit more. So the first part is the geotechnical data on the deposit. So it includes different disciplines within the geotechnical team. So mapping, joints, core logging, laboratory testing, information regarding actual deformations, creating 3D geotechnical models, and providing recommendations for design parameters. So all those values can contain external references, so a new geotechnical engineer or an expert can quickly understand where he or she can find the original data and what design solutions were used and adopted historically. If we move on to the next interesting topic, being the assessment of geotechnical risks. This is a relatively new topic in Russian geotechnical engineering. However, in international practice, risk management and risk assessment have been long trendy area and been widely used at international operations. So here I'd like to talk more about geotechnical risks at open pits. There are three high-level risk areas. One is the rockfalls and bench deformation, then stack or interim deformations, and the largest scale is the overall slope deformation. Each of these geotechnical risks can be caused by hazardous factors. The hazardous factors would include geotechnical, including various structures of different generations and extents, hydrogeological factors, including poor water pressure and saturation of the slope, and reduction in strength properties because of water presence, so natural factors, including seismicity. Then man-caused factors, those are induced loads from operating equipment or blasting seismicity. So all this is incorporated in the risk assessment. The result of risk identification is a list or register of all potential risks characteristics for specific conditions of mining. And in the future, those risks are localized as risk maps. So there are risk maps developed with indicating those risks and their levels. So how do you estimate or assess risk levels? There are various methods, and this is generally characteristic for risk management, not only in mining. There are typical methods such as the checklist approach, risk matrix, and bow and tie, and the tree event, and quantitative analysis. So here I propose to look at the easiest and simplest one with the risk matrix. So risk matrix estimate requires assessment of the risk probability and the severity of the consequences, so you can assess them both quantitatively or qualitatively. So the quantitative assessment can be presented as percentage point. So for stability, based on the range of parameters, one can define a set or range of factors of safety and develop a histogram, distribution histogram, so see how many results will have a factor of safety of less than 1. And the easiest way to assess the severity is in financial terms, in money terms, but the quantitative assessment requires a lot of complicated engineering approaches and not always clear, so the easiest way would be a qualitative assessment. There are certain patterns that can give an understanding of the approximate risk level. For example, a slope has a low probability of failure, so there are few known cases where a wall would fail entirely. However, benches fail and deform almost at in each operation, so the probability of bench failures can be medium, low, high, or very high, but the severities are going to be low because the berm widths are usually sufficient to catch all the failed material. Therefore, bench level risks will be concentrated in the top left corner of the matrix. So they can be low, medium, moderate, or high, depending on the situation and the additional factors. You can select a risk level, but assessing the overall slope risk, the probability of overall wall failure is low or very low. However, the severity are going to be very high or extreme, so the risk level for the overall slope will be concentrated on the right-hand side of the matrix. So the consequences for the risk level for overall slope deformation is going to be high or very high. It's clear that during the design stage, the risks shouldn't be high, but the pit slopes generally have at least moderate level of risk in terms of its severity. So both in Russia and internationally, those are considered to be significant and require major attention. After we've identified the risk, we need to develop the mitigation measures or action measures. If the risk is low, then no action is required. If it's moderate, then at least instrumental monitoring is required. Maybe a committee can join to stop the operation in a certain area, and then it requires long-term actions. For example, this can be additional geotechnical study or putting the walls in the final position using low powder factor blasting. For high level of risks, the people and equipment must be taken out of the danger zone, and event analysis and development of the mitigation measures are required. This is an example of a risk register. So in the left column, you can see the risks at different levels of scale. The second column are the hazardous factors resulting in the risk. Most often in the hard rock material, it's the unfavorable geospatial location of various structure and insufficient data examination are the main reasons for that. If we assume there are some unfavorable undercutting structures, the risk can be assessed as high. And after we do additional geotechnical work and we've reanalyzed this area, we can try and reduce the risk. And the last column shows the risk post adoption of the proposed actions. This is an example how you can see risk maps. So the picture to the left shows the risk map for the final pit design, so you can assess risks prior to designing the mine using the structural and geological modeling and its features. Figure to the right shows the risk map for an operating mine, but the risk levels here have not been assigned. However, the risks are described based on their type, so you can see a rockfall risk or the actual happened deformation or a potential failure. So the next slide shows a risk map also for an operating mine where the risk levels have been assessed based on a scale and quantified. So such risk maps can be placed in commonly shared areas, so all people aware operating the mine are aware of those risks. Then one of the key areas in the ground control management plan is organizing site monitoring. As I said previously, it is an interesting question. What comes first, risks or monitoring? You only think that the risks can be reassessed or identified as a result of the monitoring. So you can start with monitoring and then identify in various areas some unfavorable zones and quantify risks for those and localize those areas spatially. Risks can also be assessed prior to the design of the operation, and then based on the results of the monitoring, they can be revised. So this is an iterative process. Monitoring methods are generally divided into surface and deep monitoring methods. So surface includes those related to monitoring deformations near surface, and the deep monitoring methods are mainly related to installation of various sensors in boreholes and assumed determination of the start of the origin of deformation. So deep deformations also can also be checked with geophysical monitoring methods. One of the most modern and widespread methods that now becomes more popular in Russia and has been long used abroad is the radar monitoring. Its main benefit is that it doesn't require presence of people in the hazardous zone, even if you need to install some reference points, so it's fully automated and remote. So on this slide and in the table, you can also see how one can select the preferred monitoring methods. So depending, in the first column you can see the scale of deformation, so those vary, and depending on that the rate of deformation depends. If the deformations are small, then the speed is usually rapid, and if deformations are large, then deformation can be slow and creeping. And also the consequences differ depending on the scale. I mean, the scale of deformation within one bench, several benches, is mostly a potential risk to people and equipment. The overall slope deformation is the question to the performance and the operational performance of the mine altogether, and the preferred monitoring methods can be selected depending on the scale of the deformation and the assumed rate of deformation. Visual and radar monitoring are good for small-scale deformations and medium-sized deformation with rapid deformations. However, large deformations require expansion of monitoring methods, including mine survey and regular and in-depth monitoring, and also action plans to tackle deformations. If those are small, then you can just do scale and try and contain rockfalls. If deformations are large, then you would require to redesign your final pit design and then do reclamation or recovery work. To the right, you can see a well-known Allen-By dependency showing the efficiency of monitoring methods for short-term prevention, rapid prevention of the impact of risks to people and equipment from small deformations. So he's shown that radar monitoring gives you an efficiency of early warning of about 93%. If you add visual and mind survey reference point, then you can achieve 97% reliability. So it's not enough just to create monitoring. It's very important to create trigger levels, so how to react to those. So such a system of actions and control points, the so-called safety criteria. This is something that's called TARP, Trigger Action Response Plan. The aim of introducing TARP is to help map the provisional plan of action in case of potential exceedance of a certain trigger level. At the first level of TARP, a person or a specialist can try and remove the hazard. Reaching level 2, you have to inform your direct superior, and then a decision is made jointly. When you reaches level 3, the operation is supposed to be stopped at this zone, and the principal specialists of the open pit are required to convene to determine further actions, or those can be originally included in the trigger action response plan. An example of different trigger levels for instrumental monitoring. For each pit and operation, those have to be specific, as all deposits are different depending based on their physical and mechanical properties as well as other parameters. But one can say that for instrumental monitoring, this rate of deformation is critical. For discrete monitoring, this is measured most often in millimeters per day. For automated, it's millimeters per hour. And the actions for different trigger levels. For the first level, the specialists or monitoring team can check whether this is a false alarm or whether they can see trends. If it's a false alarm, then it's being cancelled. If you go into the second level of the trigger action, then other specialists of the pit are informed, and such actions can be taken as more high frequency monitoring, and the deformation area is assigned a higher level of attention, and reaching the third level, the people and equipment have to be removed from the hazardous zone. Apart from instrumental monitoring, visual assessment is also a tool. So safety criteria for visual assessment, one of the examples would be simplified indicators of potential hazard, using which every person in the pit can define and log its observation, his observations, the opening of less than 5 meters or 5 to 10 centimeters, and seeing deformation of certain blocks at the crest of a bench. If a person sees that, then he can inform his direct superior and stop operating in that area until the reason is identified. Another example for visual assessment as part of TARP are the rockfalls. If it's once a shift, then this is something that's worth attention. If the rockfall on the bench slope happens several hours per hour, then it is a reason to temporarily stop the operation and go on wall control measurement plans that are defined during the risk assessment exercise. By the way, the reason why it's called stability management, not ensuring stability, there are actions that are meant to stabilize and improve pit slope stability, and there are actions that do not propose making open pit slope stability, but are meant to minimize the negative impact. So, for example, if we set the rockfall protection measures, then you can make the berm narrower, and there are examples of that internationally. However, the stability of the overall slope will not increase, but the safety is being created by additional measures implemented. Also, another stability improvement measures are creating buttressing and use of support systems, horizontal drainage, optimizing drill and blast parameters. So, for example, if we use low energy blasting and slope stability is improved. Each action is supposed to have a plan for mitigating potential risks when implementing those actions. The key idea here, I think, is that if we see, based on the risk assessment results, risks are being high, it's important that the risks are eliminated before the pit slope gets in the final position when those risks can materialize. If high risks are identified based on monitoring results during the operation of the pit, then measures are developed, rapid implementation measures are developed to try to minimize those risks to high risks, to moderate or low. And finally, last section is the risk management at the mine site. The key points here for organizing risk management system is creating a geotechnical team at the mine. So here on the slide you can see the main functions of the geotechnical department, but in general I would like to say that the geotechnical team can be divided into two main offices. One is the analytical and the second one is the monitoring, to actually do the monitoring work and accumulate geotechnical hydrogeological characteristics. Another part of the risk management system would be engaging all of the staff of the operation of the open pit into risk management. So the technical manager should make sure that all the hazardous factors regarding slope stability have been identified and are controlled at an acceptable level of risk. For example, pit foremans are required to make sure that all the pit personnel are aware and have been informed about the potential risk, checking the slopes for any loose material. Other pit operators are required to follow safe operation practices, inspect rock mass checking prior to and in the course of their work. And finally, regarding the corporate policy on implementing GCMP is in the fact that information regarding the rock mass and the risk identified is presented on electronic displays or information boards, so that all pit operators and pit personnel can see that, and regularly during the meetings on slope stability and action response plans and remediation measures, those can and should be discussed. GCMP also sets out the document exchange between different departments of the mine. Geotechnical specialists have to have regular sessions with the pit staff and should undergo advanced training as well. As external experts should also be involved in order to identify and highlight potential ways for improvement of that. And that would be all from me. Thank you for your attention. If there are any questions, I'll be happy to take those. Yes, please.
Меня слышно, да, теперь?
Colleagues, can you hear me now?
Прекрасно.
Алло. Да, слышно.
Okay. Yes, Sergei Volkov, Mankasei Zolota. One question. Is there such a factor as influence of wall stability as the speed of development of the open pit? Well, the speed of development, the rate of development, is certainly a factor, but I think this is a minor factor, at least in hard rock. At least in geotechnical assessments, this factor is not included. I think the life of the exposed slope is something that serves. If it's a short-term slope, then other design criteria can be used. For example, factor of safety can be reduced as a criteria, but how to incorporate that factor, I mean the speed of development, So intensive during blasting and intensive haulage doesn't have an accumulated effect on slope load. The work intensity, I think, has a little effect. Well, intensive blasting certainly does have an impact, but if one uses wall control and pre-split operations, I think creating the slopes in the final position won't have a lot of impact, and we don't know how to assess that. If I can add, colleagues, on the answer, if you can hear me. I don't understand if you can hear me or not. Yeah. Yes, we can hear you. Yes, I would agree with what Victor said, is that the rate of advance, I think, wouldn't have an impact on stability. Mostly. Why? Because we talk, it depends on the rate we're talking. How quickly do we mean? If it's the 5 years quicker on one schedule than on another schedule, I think we can incorporate that in terms of the life and the rock properties of the slope. If we talk about months, I don't think there is a sense in that. Second factor is that geotechnical estimates and all software packages do not take into time into account. They do account for a staged approach. If there is or there isn't time in domain to that. In terms of during blasting operations, I believe that when blasting, it's the milliseconds between delays that are estimated, which is enough to break the chain of instantaneous impact. If we talk about if we blast faster in a block a month or a week ago, so if we talk about a minute or a month, I don't think that will have a major impact. Thank you. If there are no questions, no, there are questions still on the floor. We'll take another question, and if we could ask to leave other questions after the call or in within the surface. Victor, you've mentioned that radar is one of the most effective methods of monitoring. What manufacturers could you recommend, and what should be paid attention to? Well, I wouldn't really be advertising any most efficient radars because conditions differ, and they always are. If it's a provocative question. It's a provocative question. But altogether, pits without significant geotechnical risks and the one that's mined over a short life, conventional systems can be sufficient. You don't have to introduce radar monitoring. In terms of adopting specific systems, I think it's to everyone's taste, like survey methods, like some surveys usually go for Trimble, others for Leica, but this is a kind of a habit. If the tool is efficient in what it's supposed to do, then I think it's to a specific taste of a person. But in terms of the accuracy of scanning, I think they stand more or less on the same level. All the major manufacturers, the ones that I know, maybe there are new developments. I know IDS, Ground Probe, and Roytalk. Are the three major ones I know, and I believe that all three companies have, in the Russian operations, use equipment from all three manufacturers. Colleagues, if we can move to the next presentation, I would appreciate if you could ask the question at the end of our masterclass, or maybe catch him outside of this forum. I would like now to give the floor to Ivan Biruchov. He's going to be presenting from the mine site, so we won't call the name the deposit, but we can move to his presentation now, without saying which side he's on at the moment. Afternoon, colleagues. Glad to greet you all. However, they're telling me that I have only 10 minutes left for my presentation, so I'll try and be very brief. So, I hope you can see my screen. I don't know. Yes, we can, and we can hear you, so go ahead. So, colleagues, I'd like to pay your attention to the following areas. Victor has covered the main points. I would like to note that GCMP is a tool to manage the mine, and it regulates the actions of the mine staff, those responsible for specific execution of the plans, and those that are aimed at changing the condition and the status of the rock mass. And the GCMP itself includes all information pertaining to managing rock mass behavior, and one of the functions there is to regulate the actions of the geotechnical team at the mine. So the main points, GCMP really covers the process for the development of the geotechnical models and their verification and the design process, geotechnical justification of design solutions, and then training and control of the processes, and then monitoring and regular inspection of the mining operations. I'd also like to note that this document, the GCMP itself, is supposed to be a single, live and logical, simple to use document, and it is reviewed in case of any unexpected accidents or incidents, or in case of changing strategy, or when the mining sequence is changed, when we say expose some unknown geological structures, and then we have to revise our own processes internally, so following the changes in the geology. So the elements of the GCMP is what I've already covered, and Victor described that in a lot of detail. I'd like just to name them. Safe operation depends on identified risks that are always at the cornerstone and development of the geotechnical models, planning of the mining operations, monitoring, validation and calibration, then execution of the design, and following the design during the development of the deposit. And the most important point, I believe, is the interaction between various disciplines, as this is not only pertaining to geotechnical engineers, but the mine altogether. How the different departments cooperate and how they exchange information, and this tool should be covering that and simplify that as much as possible. And then training and audit of the GCMP and the processes that helps us to simplify all that. So that would be in brief. There's the risk identification, is what Victor did devote a lot of time to, and he did rightly so, regarding the risk and hazard register is fundamental to mine design. So it is a cornerstone, and everything else should be running around it. And this process, the other process will be based on that. Regarding hazard identification, Victor also mentioned that there is a number of techniques for risk identification, and the company itself decides what they're more interested in. Is it the quantitative or qualitative risk assessment, and how, following the preparation of such risk register, how do we manage those, or how we manage those risks, how effectively we manage it, whether those actions are actually helping us to manage those, or we accept those risks and agree that they exist and we work in those conditions. For example, we can't remove water from the rock mass, and these are the inflows we get. So we either buy pumps and pump it out, or we work in wet environment, but at least we understand that. Then geotechnical model. Here, Victor really did provide a lot of explanation. I'd just like to add here is that the sufficiency, the model itself depends on its quality, on the quality and the sufficiency of data that are used to create that model and the level of detail that the model has also varies depending on the geology. So for some operations, geotechnical drilling on 100 by 100 meter spacing is sufficient because of the strength properties and variability of other properties. So this is all site-specific and something that needs to be borne in mind. I also like to note that on the geotechnical modeling, I understand the lithological model, structural model, geotechnical block model, then numerical stress distribution model, and the hydrological model. Victor mentioned that the new federal norms and rules include additional terms such as geotechnical information model. And if there's an opportunity, I think Victor can give more detail on that later on. Regarding the design, so GCMP should include and understand the approaches and techniques that we use to assess stability. So now we can use the whole range of methods available, the kinematics and numerical modeling, so we're not limited or constrained to any specific techniques, so we can use the entire range of tools regarding the monitoring and control. I think Victor did touch on lots of those. I won't step on that too much. It's the one thing is the TARP, the trigger action response plan, really is important. So if monitoring shows us, and it should clearly indicate to us if we do a survey and we see a deformation or roof deformation of 5 centimeters, we can just keep monitoring. If it gets to 10, then we need to maybe provide additional support to the roof of the development, so we do something else. So if we see that the deformation continues, then we either close off or make the roof collapse, and then we support it again. So all of that should be covered in the trigger action response plan, so the surveyor understands and the geotechnical engineer can understand and interpret monitoring results. And the monitoring plan is developed on the basis of the models. We can zone the deposit and identify potentially hazardous areas, so the monitoring plan can be overlain and to keep closer eye on specific areas, and the GCMP describes all that. Regarding the interaction between different departments, we understand that a lot of teams are involved in efficient operation. If you look at the job descriptions for geologists and geotechnical engineers, you will see a lot of duplication, that the geologist does face mapping, the geotechnical engineer does that as well, and same relates to core. So I think we can combine that, and at the operational level, those can be optimized. Similarly, regarding people and ways of using information. So information being provided as input and how we use that. So we take geological data. Well, first of all, we get a request from the miners. So whether the development is going to be stable or not, so we need to take the data from the geologist, interpret that, and then pass it on to further on. I'll hope to touch on that in more detail later on. And in terms of training, this is also important, and Victor's also discussed that in detail. I would like to know that training is not only for geotechnical team and its advanced training continuously, but training all pit staff or mining area operation staff involved in doing work in those areas, and the staff should always be informed and competent, informed of those risks and competent to act accordingly. Here, if I may, I would like to also discuss what GCMP should contain, or how this starts in terms of creation, in terms of structure. First is general information, so you don't need to provide a lot of detail, just the mining history, natural geological conditions, then roles and responsibilities are highlighted. Ivan, this is Alexander Makarov. I will talk on that, so you can stop there. I won't go in detail, just a brief. Then we describe the current mining situation regarding the mine layout, the development plan, types of support used, so what is actually used at the operation. Then the same regarding the hydrogeology of the deposit. Then we discuss the acceptance criteria or the failure criteria, so the physical and mechanical properties and the strength passports. So what geotechnical engineers use as the basis, and the geotechnical model. As I mentioned earlier, this is the structural lithological model, block model, and the rating characterization of the rock mass, then hydrogeological model, and the in situ stresses on the mining, now on the mine design, the current plan, and the major mining parameter, critical key mining parameters, and the techniques used for stability analysis. So this should be set as macros, so that the geotechnical engineer wouldn't spend too much time on doing that, but rather spend more time on interpreting that. So he or she should know about that, and the GCMP should have a page there, a description in the GCMP on that. I know I'm 2 minutes late, and then it's monitoring, data collection. This is also regulated and controlled. Everything's prescribed in the procedures for underground development logging. It's a separate standard for core logging, also a separate procedure. Then next, regarding risks, we highlight all the risks and have a more detailed description, all of that, and the operational control and reporting. So all of that should be simplified as much as possible, so that geotechnical engineers wouldn't need to spend too much time on that. And this is, colleagues, where I think I'd like to end. Thank you, Ivan. If there are questions, we do have time for one question for Ivan. If not, then we can leave them until the end of our workshop. I don't see the room, but are there any questions in the room? Good afternoon, colleagues. I will take over from Ivan Birichov, but in the format of a case study for an underground mine, one of the underground mines which has a well-developed ground control management plan that has repeatedly, successfully been audited by specialists from Australia and Canada, and I believe this is one of the best plans I've seen in the CIS countries over the recent years. This slide shows the structure of this GCMP. Please pay your attention the sequence of what is included in the GCMP. Please pay your attention to the volume of that, so it's over 200 pages long, including more than 90 charts, figures, photographs, and another 26 tables with criteria and the layouts and the. So let's begin the structure of the plan, the purpose and its applicability. So this is a management plan meant for personnel responsible for operations related with risks of rock falls at surface and in underground development. So this GCMP defines the key requirements to what and how the operation should act at the mine, those involved, starting from the miners to the mine manager and the overall operations manager. So this plan also outlines the roles and responsibilities of all staff involved in ground control management, starting from the operations director, making sure that the staff is properly trained in ground control management, that there is sufficient funding for this plan to be implemented, that geotechnical aspects are adequate in terms of the mine operation and future development. Chief engineer of the operations should make sure that it operates in terms of following legal requirements, and it's all implemented in full, and all geotechnical aspects are adequately implemented in the designs and reflected in the designs and the mining technologies. That audit and assurance of execution of the GCMP are in place. The head of the geotechnical department is responsible for all the rest, the collection and interpretation of initial data, development of the GCMP and all mining facilities, accounting for all potential factors that may result in the rockfalls and deformations, inspection of all major incidents related to that, interaction with all technical divisions of the operations, reporting to management, as well as regular audits and checks and reviews and quality assurance, so on and so forth. This GCMP provides detail what people are required to do, the surveyors, the geotechnical engineers, and the mine manager, chief engineers, so down to the underground or surface miners. So here we say that our major risk is the risk of the rockfall. At this operation, the case study is based on the risk assessments being done using the rainbow tie method, and Victor in his presentation discussed the risk matrix approach to that. So here I'd like to tell you a bit more about the different methods for risk assessment. It's the rainbow tie approach. Bow tie approach. So the approach used at this operation to have identified material adverse impacts, and the main one and the most widespread would be the rock falls in underground developments, also air blast, and also pillar failures, so sinkholes, and also wall instabilities if that happens when mining operations are carried out underneath the open pit. So here you can see the structure for review of risks using the bow tie approach. So here you can see that mining operations result or creates the risk of rockfalls. As a result, it's legally required that mining operation is hazardous by default, and it is associated with one of the major risks being the rockfall. So column to the left in red, the reasons that are the sources of risk of potential rockfall. So insufficient support, incorrect assessments of the rock mass, inappropriate installation of support, the rock pressure resulting in deterioration of the support, and material displacement. Those are the key risks, or the key sources that create the risk of the rockfall. So each risk is followed by the green boxes. Those are barriers or constraints that can help mitigate or limit those reasons. For example, insufficient scaling the potential measure to prevent that, help eliminate this, would be staff training by proper assessment of the rock mass conditions or proper scaling, and also presence of means and equipment and time to scale those loose rocks, and so on and so forth. Each reason, each source, purpose has its barriers that can help mitigate those reasons for rockfalls. So following support designs, provision of sufficient materials and equipment, inappropriate assessments of the rock mass conditions. So this is an error of the geotechnical engineers of improper assessment of the stability of the rock mass. One of the barriers would be advanced staff training and providing tools required for that. Inappropriate selection of the support type. So this requires regular review based on results of the incident and accident audits, our support designs, and we know that the mining and geological conditions change over time. For example, when we get deeper and we are in different mining environment now, those can be related to maybe significant depths, or we are now in the rock burst hazard area, and this is done with account for changes in the mining and geological conditions and inappropriate installation of support and all other reasons for potential risk materialization. The company, together with us, have developed those barriers, constraints that help mitigate those potential reasons. To the right, from the actual rockfall event, you can see the barriers that are meant to mitigate or reduce the consequences of the rockfalls. So the ones to the right are barriers aimed at reducing the frequency and the probability of the rockfall. The barriers to the right are those that can help minimize the consequences of the rockfall. My apologies. I have to take that. Alexander, we've got very little time, just 7 minutes. Okay, I'll jump forward. So the GCMP assumes developing a risk register for rock stresses and the damage from those. So, the first is the injuries, loss of developments, the need to develop new workings, losing balance reserves, losing ore in pillars and dilution. One of the most widespread risks is causing injuries as a result of rockfalls. So this slide shows the frequency. Apologies again. I have to answer the door. This Western Australia, one of the most developed operationally, it's the frequency of fatalities per 1 million of man-hours. You can see that in the recent years, there's metrics being reduced. This is a result of mining companies tackling the issue of ensuring safe operations. In Soviet Union, we used to use the injury frequency rate as a number of injuries per 1,000 man shifts. This slide shows the benchmark And so the best examples that international companies try to align to in order to ensure acceptable level of risks at underground operations. In 2003, that level was 0.08. So that's there. Number of injury per million man-hours. In 2013, the best practice reached 0.03. Australian mines, with the acceptable risk is considered 1 multiplied by 10 to the minus 4. This is the number of injuries throughout the year divided by the average listed payroll in that year, staffing level. So, as an example, in Australia, 22,000 people involved, including 15,000 in underground operations. The number of fatalities is 1, so that takes you to 0.067 by 10 to the minus 4. Of all the fatalities at underground operations, the largest proportion in Western Australia were the rockfalls. So as you can see on this chart, it's about 40%. Approximately the same rate is observed at Russian underground operations. The scale of the rockfalls vary significantly, starting from individual loose rocks in covering just several square meters, down to large-scale failures at large operations with long operating history, hundreds of thousands of square meters with man-caused earthquake and air blasts. So the highest scale. So the most common risk is the rockfalls, and scaling is supposed to resolve that and providing support in accordance with the design. The higher the scale of the rockfall, the less frequent it is. So at a small scale, there is high frequency of rockfalls, but large-scale failures are rare. So over 10 years of Western Australia mine operation history, the distribution of rockfall based on the scale, so man scale, so those are individual loose rocks. So 66% in terms of the truck and in terms of a slope scale. So you can see that the individual person risk is the major one. Most often people get injured directly next to the face, not further than 10 meters away from the face, and usually it's less than 2 tons. So small scales, quite often and close to the face, is the key, is the most dangerous area. So this is the highest risk that we have in underground operations. The procedure for managing this risk is scaling, inspection visual, to identify remaining loose materials, and supporting and monitoring your support and repair or reinforce if required. If there are indications that the rock mass is still active and it continues developing. And then regarding further GCMP, you would describe the responsibilities of all the mine staff regarding specific risks in terms of ensuring safety. The mine management should ensure stability of all developments where staff moves, then training for safe scaling, availability of tools, PPEs for scaling, and time needs to be taken into consideration. So all the mining schedules and development schedules are required to incorporate time for this work. Then this specific GCMP also outlines the responsibilities of the mining areas supervisors. than the foreman and the miners, including training on the ways and means of assessment and identification of hazardous factors at the workplace. And then these are the indicators of potential risk of rockfall. Experienced miners would know them all. Finding new fractures and their further development, then rock bumps, movements, displacement, unfavorable orientation of the joints, presence of weak or crushed material, indications of weathering and presence of water. Water never served good for miners, only makes our life more complicated. Another indication here. Alexander, I think we're running out of time. Just about to finish, and all methods for scaling should be safe. If ensuring manual scaling is problematic, then introduction of equipment for scaling should be looked at. There is a wide range of equipment available for that to make to provide safe operations. So you can see the hydraulic hammer there to remove that. An interesting way was pursued by Kazakh mice. They used a different one using like bear paw approach. So loader was equipped with kind of a mast that rips the outside of the development and the movement of the loader, as well as the move of its hydraulics. So it's about 6 tons pressure applied. So such a loader with small scale bucket in developments. And when this equipment operates, these traces remain. So when I see a fight like that, I know that it's been properly scaled and you can access it with significant level of certainty and low risks. That's all from my side. Thank you for your attention. If there are any questions, I'm ready to take them. Colleagues, hi again, those who haven't seen me before. Thank you, Alexander, for your presentation. I've recently myself seen that equipment, and I've seen how rigorous it is and the safety that it brings. Colleagues, if there are any questions, I hope organizers will give us time for a couple of questions. I think we're only 3 minutes behind our schedule. If there are questions to Alexander, please ask questions to Victor. I think you can catch him outside of this masterclass. If you have questions to Ivan Birichov, I think you can talk to Ivan on that. Are there any questions at the moment? Yes, we do have the question, but we don't have the microphone. Can you hear us? I can almost hear you, but it's good to hear that. I hope you can hear me better now. It's wonderful. That's regarding the software that you're using for geotechnical modeling. Is this a range of different software packages? Is there anything you can highlight? Well, I can take that, Alexander. Yeah, sure. So in our experience, we use almost the entire range of software available, commercially available. We try to be involved in all of that and try different packages depending on the tasks that are set. If we talk about some geological modeling, then this is a well-known package like Leapfrog, Micromine, but mostly geotechnical is it Abacus or ANSYS. We mostly use rock science. If this is not enough, then we can always add up MIDAS. That's in the SRK Russia office, but we also have opportunity to engage people from other offices who are skilled in our task software, 3DAC, Fleck 3D, and other. So the entire set. If we talk geotechnical modeling, in our experience, we have not used abacus, frankly speaking, and we don't use Plaxis. If we talk about finite element modeling, so this will be MIDAS and RS3, rock from rock science. That's good, thank you. But your scale of your models vary a lot from regional scale to very local ones, right? Well, depending on what you mean by regional, maybe the mine level, like the license area. If we talk about underground operations, for as an example, depending on the aim of that, certainly. And question to that regarding the physical and mechanical properties, what is your scale? How do you scale that, or do you somehow validate that on site? Because the core and the rock mass are different things. Yeah, we understand the question. We always try to calibrate the models and we accumulate data. In any case, we have a geotechnical block model, and we understand the geotechnical domains based on that. And within those domains, we have all the geotechnical rock properties. If its accuracy certainly depends on the inputs. If it's a greenfield operation, there's nothing to calibrate against. But if we have developments already, then we can adjust those and calibrate using those. And we try to, transition from sample results to based on the monitoring. But there are also interesting tasks. The mines have been mined for 200 years. There are ones operating for more than 200 years, others for 100 years. Creating a model for such operation for the entire minefield at the current state of technology development, we believe is unreasonable. If we talk historically, we can incorporate that, but it's a question of if we really need that. If back calculations are required, then we can do that as well and do some back calculations based on that. But we always try to use reasonable sufficiency approach in our work. If this is really required for practical purposes and one would see the benefit of doing that, then we will push to achieve that. If we see that something is too long or too expensive with little benefit, we try to discuss that with our clients, what it is exactly that they need. Okay, thank you for your response. That is clear. I think we're over the time now. I understand that it's very little time that you have to have your coffee break, what's next in the agenda, but thank you all for your attention. If you have any questions left, first of all, Victor, you can always find Victor to ask him questions, but we've got the contacts of our representatives, and there's going to be SRK booth at MINEX. And I'd also like to note that the last thing really is that there will be an opportunity at the booth to test our new development in terms of mapping structures. This is our development of our Canadian office, and we're now quite actively testing and trying to use that. If you can come to the booth, I hope I am correct. I haven't been to the office for a long time now, but I do hope that everything's been worked out and you could try and use that personally, visiting the SRK booth. That would be all. Anyone to add anything from the speakers? But we're 10 minutes over already. Thank you all. And with that, I'd like to close.